The second talk is by Peilin Zhong on massively parallel algorithms for high-dimensional Euclidean MST.
Okay, thank you. Okay, so hi everyone, I'm Peilin from Google Research. Today I will talk about massively parallel algorithm for high-dimensional Euclidean MST. This is a joint work with Rajesh Jayaram, Vahan, and Chen Narayanan. Okay, so I guess most of you already know what is the Euclidean MST problem, but let me briefly recap what's the problem formulation here again. So given a set of points in the Euclidean space, in the d-dimensional Euclidean space, so n points each has dimension d, then we can regard this as a complete graph over these points. So the edge weight between 2 points is just their Euclidean distance. And then we want to find the spanning tree of this complete graph such that the total edge weight is the minimum. So in the approximate Euclidean minimum spanning tree problem, we want to find the spanning tree such that the cost is at most alpha times the minimum spanning tree cost. This alpha is the approximation factor that we want to achieve. So in this work, we study the Euclidean MST problem in the massively parallel computation model, the MPC model. This is an abstraction of many modern distributed parallel computing systems. Let me close the. Okay. So it's an abstraction of MapReduce, Flume, Beam, and others. So in particular, in this model, there are P machines. Each has local memory S. The computation processing runs. At the beginning of the computation, the input is distributed arbitrarily on several input machines. And then in each round, each machine can do some local computation based on the local data. And then at the end of each round, each machine can send arbitrary messages to other machines. However, there's one constraint. This is that in one round, the total messages that one machine send or receive cannot exceed its local memory. This is because otherwise it cannot store the data locally, right? The goal of developing efficient MPC algorithm is that, firstly, we want the local memory usage is as small as possible. So because the local memory is always bounded. In particular, we want the local memory to be into some small constant delta. And then we also want the total space used in the entire system. The system for this algorithm is near linear in the input size. That is to say, the number of machines times the memory per machine is near linear until the 1 plus some small constant. And most importantly, we want our algorithm to be efficient, right? This means that we want the number of runs of our algorithm to be as small as possible. So usually we desire better than logn number of runs. We want small of logn number of runs. Okay, so let me briefly introduce what's the previous work. So for the low dimension space, Euclidean MST, then Andoni et al. Shows that there's a constant number of runs, 1 plus epsilon approximation MST algorithm in the MPC model, and it only uses linear total space. This is super cool. This is very desirable. However, when we consider high dimensional space case, then the problem becomes hard. So all the previous approaches either uses so all the previous approaches uses 2 categories of the methods. Both of them use kind of the location hashing. One type of approach is spanner type of approach. Another one is the tree embedding based approach. Let me briefly introduce what's the spanner-based approach. So in particular, we want to build a sparse graph such that for any 2 points, 2 nodes in this graph, their shortest path distance is a good approximation of their original Euclidean distance. And then the previous work, the hierarchical Indic and Polis, they have this solo paper. They show that they can use the location hashing in constant number of runs, and then you can build this sparse graph using until 1 plus delta number of edges. And this can be computed in constant number of MPC runs. And after you get this graph, then what you need to do is you just need to output MST of this graph. Then use the standard MST algorithm in the MPC model, then you can achieve logn number of rounds. And because the spanner has a constant approximation, so you have a constant approximate MST. However, if you do not use any additional information, once you have the graph, you just look at the graph itself, and then you try to compute the MST of this graph, then this logn is a barrier unless this 1-cycle, 2-cycle conjecture is false. So this means that if you want, so given a graph, and then you want to compute the connect components of this graph, if you want to compute the connectivity of this graph in the MPC model, then you need omega logn number of rounds under this conjecture. Okay, so this is spanner-based approach. Another type of approach is the tree embedding type of approach. So the idea is that we want to embed the original Euclidean data points into a tree, such that for every 2 points, for any pair of these points, their distance over the tree is a good approximation of their original Euclidean distance. So once we have the tree, this automatically gives you a spanning tree. Then the approximation ratio is the distortion of this tree embedding. Then the question is that how good is this? What's the best this distortion? So there's previous work shows that okay, so there's you can easily get a logn square distortion, and recently the STOC 2022 paper, then they show they can improve this to the logn approximation. However, there's a lower bound. Bartle shows that actually, if you just look at this tree embedding, then you cannot avoid this omega logn distortion. So this means that your best approximation, your best distortion here is logn. So you can get the constant number of rounds algorithm, but you cannot avoid this logn approximation ratio. So if we look at the previous results, for the low dimension space, it's pretty good. For the high dimension space, so we either need logn number of rounds, or the approximation ratio is logn. And for the spanner approach, if we do not use any other information, then this logn number of rounds is tight. And for the tree embedding type of approach, if we use the pure tree embedding type of approach, this logn approximation is also tight based on the lower bound. Then what's the cure? So we show that actually we can combine both ideas. So actually tree embeddings uses the geometric information, and spanner is more fine-grained locally. So we just combine these two. And then after combining this, we show that we can achieve logn number of rounds. So logn number of rounds and constant approximation. So here's the main result of our work. So we can get a constant approximation to high-dimensional MST using logn number of rounds. And our algorithm is fully scalable. That means that our local memory is sublinear in the input size for any constant delta. And our total space is near linear, is n to the 1 plus delta for arbitrary small constant delta. And also, we also show that actually we can also give a constant approximation to the TSP, the traveling salesman problem. Although you may think about that the MST can directly imply TSP results, but the answer is no, because imagine you have MST, which is just a pass, and then if you want to output this pass, if you use the standard unilateral algorithm, use the doubling algorithm, you need logn number of rounds. And we show that actually using the geometric this structure, we can output this pass in logn number of rounds as well. But due to the time limit today, so I will not talk about the how to get this TSP. I will mostly focus on how to get this MST. Before I go to the technical details, let me first talk about what's the key technique and the takeaway message here. So the high-level idea is that we first create a Euclidean spanner graph. Then we try to run the MST algorithm. However, instead of compute the entire MST, we just use this. We just iterate log number of steps. So you can imagine you may have some subcomponents, some small components, and then we use this geometry information and some this random space partitioning technique, and then we can complete. Then we can have a way to merge this subpart. And so basically, in one sentence, it's just combining graph algorithm with the underlying geometry. Okay, so now let me start to talk about more technical details. Our starting point is the standard Kruskal algorithm. So let us first define the T-threshold graph. So T-threshold graph is as the following. So this graph is over the entire point set, and then we connect to points if their distance is at most t. Then the Kruskal algorithm can be described as the following. So at the beginning, your spanning tree set, the edge set, is empty set. And then you just smoothly increase your threshold. And then when two connect components, they're connected. And then you put this edge into your tree edge set. And then finally, you can get your MST. Then one idea for the parallelism, so how do we get log number rounds, for example? Instead of smoothly increase your threshold, you can only look at this discretized edge weights 1, 2, 4, 2 to the I, and to the largest this diameter delta. And then you at the same time compute all the edges with the same edge weight at the same time. And then if there's an edge connect the two connect components, then you just add it into your tree edge set like this. And then so we can use the BFS to find which kind of edges that we add to them. And then finally, we can get a constant approximation. This is because if we just round up by to the discretized edge weight, then it will only lose a factor of 2 factor. The first question is that then how do we run this BFS in the MPC model? So this is relevant to the connectivity problem. So there's a very standard trick is the leader compression approach. Basically, given a graph, and then you want to find these connect components, what you can do is that you sample leaders. So for each node, with probability 1/2, you sample as a leader, and with probability 1/2 as a non-leader. And if a non-leader has a neighbor, which is a leader vertex, then you can just choose an arbitrary leader neighbor to merge. And then in this way, you can imagine in every round, you can, in expectation, reduce 1/4 number of nodes at least. So if you do log number rounds, then you can definitely find the connect components. Here's the leader compression algorithm. And notice that another key observation is that if you do not do log number rounds, if you just do R rounds, for example, as I mentioned previously, because in each round you can reduce 1/4 fraction. So after R rounds, you can reduce the number of nodes by 2 to the omega R, this factor. This is a very important observation, so you should keep this in mind, because later we will show this how we can use this to save a lot in our MST algorithm. Okay, so here are some challenges. So in the previous slides, I showed that okay, you look at this threshold graph, but the first thing is that if you look at this threshold graph directly, you have n squared number of edges, so you cannot really work on this graph. Then what's the idea here? So we can replace this completed graph by a spanner graph. As I mentioned, you can use the logarithm hashing to create this kind of spanner graph. It only has n to the 1 plus delta number of edges, and it has a constant approximation. And most importantly is you only use constant number rounds to compute it. Another issue is more crucial. So as I mentioned before, the leader compression algorithm itself, if you want to find the whole connect component, then you need log number of rounds. And to find the connect components, it's hard to get a faster algorithm because there's a 1 cycle, 2 cycle conjecture. So this conjecture means that if you have just like the graph which is 1 cycle or another graph is 2 cycle, if you want to distinguish these two cases, then you probably need logn number runs. Then what's our solution here? As I mentioned earlier, so we can use the geometry information of this Euclidean space. Okay.
For the leader compression, can you just, when you said that you want to go from n squared to the 1 squared. So for leader compression, can't you just say that if I have a lot of neighbors and even with very high probability, one of them will be a leader?
Oh, right, but you do not know this graph structure, right? So, for example, for some nodes, you may have high degree, and then your some node is very very sparse. If you only have like constant degree, then you only have constant probability to merge this, right? Is this your question, or?
I wonder if you can just argue that the space is almost linear.
Oh, I mean. The leader compression algorithm, there's no space issue. The space issue is just like if you look at the exact threshold graph, then you have n squared edges. For that part, we can directly use the spanner graph to resolve that. Yeah. But the issue of the leader compression is that if you want to use the leader compression approach to find the entire connect component, then you need logn runs. Yeah. Okay. So then how can we boost this leader compression this step? So how can we boost to find the connect components? Then we can use this kind of quad tree to boost. The idea is that now I look at the edge with distance t. Then if we look at if we partition this kind of space into cells, and the side length of this cell is t over d, then we know that if 2 points are in the same cell, then absolutely their distance is at most t, right? Then we can just merge them together. So what we can do is that we have this kind of like the quad tree, this kind of structure, and then each cell has length t over d. Sorry, just have this kind of grid structure, and then each cell has this length t over d, and then we merge them together. So we have some contracted connect components, sub-connect components. And then starting from this contracted graph, and then we run the leader compression. So here, then Indic has this lemma, shows that there's a relationship between the number of supernodes. So it's just after you have this kind of relationship degrees, then how many cells are still non-empty. So this is non-empty cell. Then there's a relationship between the number of non-empty cell and the MST cost. So intuitively, why this is true? This is because if you look at each MST edge, then what's the probability that this edge is cut by this kind of like the boundary of the cell? It's roughly the edge weight divided by the cell length. So you have some d over t times this MST. Actually, I do not care about the exact number here. What I need to know is that, so I can use the JL to reduce the dimension to logn, and delta is polylogn. The delta is poly-n. So after log is something like logn. So it's something like your number of supernodes is polylogn over t times your MST. Okay. Then what does this kind of like the observation can help? Why this can help us? So now you can do the following. So you look at your supernode and then try to run your leader compression, and then after logn number of runs, then you can know that your number of so if this connect component has largely if it's not contracted to a single connect component, then you know that the number of nodes is reduced by 2 to the R factor. R is the number of runs, as I mentioned before. Then how can we use this kind of information? So if this connect components, they're in a cell such that, for example, it's polylogn times t, then we can connect them arbitrarily, Because this is because we already make a lot of progress. We know that there's large number of supernodes, and then we reduce a lot of them. So we know the MST cost is already very large. This means that I only need a few number of edges to connect the remaining of them. So this edge should not contribute too much to the MST. So here's the idea. It's basically the formal proof of my this kind of like the intuition. So basically, you can show what's the number of this supernodes you have, and then after this number runs, then you reduce the number of connecting components, and then you can show that actually the new edges, the final arbitrary edges you added, is the MST over very large polylogn. It's based on how many previous leader compression runs you want to have. Okay, then here's another question. So how to ensure that the diameter of this connecting component is at most the cell length t times, or the threshold that we consider t times polylogn. So this is very hard. Actually, if you do not have other constraints, this may not be true, because you can imagine you can have a very long path that though you already have this kind of like supernode, but then this path can be very long. So the diameter of these connecting components can still be very large. So how do you do this? Then we can add another constraint. So we can impose a second larger this kind of hypergrid, this right line. So you can imagine this, the length of each cell of this larger grid is much larger than t. It's much larger polylogn times t. Then what I need to do is that when I do the connecting components, I restrict myself in these large cells. And the reason why this works, because you can imagine with very small probability, the edge with length t will be cutted by this kind of like this right line with this higher cell. And even it's cutted because you only have a very small probability to cut it. So in expectation, you can afford that. You can just raise the weight of that edge and then and use that for in the MST edge for a higher edge weight. Then once we have this, once we have this constraint, then we can safely do the connecting components inside each of this kind of large cell. Then after we do log number runs, and then we know that each connecting component in this ratio, the diameter will not exceed by t times polylogn, then we can connect them arbitrarily. Okay. So based on this observation, then we already have an algorithm to solve this gap instance. This means that given a Euclidean point set, if you look at the pairwise distance, their distance instead of 1, 2, 4, 8, they have a very good this kind of like the separation. If the 1 alpha square, alpha cube, to 2 delta, this alpha is a super large polylogn. Because in this case, then you can have this independent, this kind of like the levels, and then for each part you can independently run the connecting component for each edge with threshold. Then here's another challenge. So now the things that given this, so in the previous slide, given this one, so you have this kind of like the red line, right? You have this kind of like the large cell, and then I say that you can just safely connect all the sub-connecting components that they're in the same connecting component. You can arbitrarily connect them. But the question is that how do you know they're actually in the same connecting component? Actually, we do not. We do not need to know whether they're in the same connecting component. This is because, if they're in the same this kind of large cell, because we already run enough number of the leader compression, so we know the MST cost is already very large. In this case, we can overmerge this kind of connecting components, even though they are not in the same connecting component in the T threshold graph. So after we run log number of leader compression, we just connect all the subparts inside this large cell arbitrarily. Then in this case, we can resolve this kind of like the consistent issue. We just do the overmerge. And then the final thing is that how do we handle the weights that is not one, which is not the gap instance. Now let's consider the full instance. We have the edge weight from 1 to 4 to the I. Then in this case, we can do a similar idea. So we first look at edge weight, which is 1 alpha. Alpha is the large polylogn. So 1 alpha, alpha square, alpha cube, 2 delta. And then now at least we know which edges we should choose for this edge weights. Now we have some bottom connect components and larger connect components. And then if we look at the middle edge weight, then we just need them to be consistent. Then we can do divide and conquer, and then we apply a similar leader compression approach. Then finally we can resolve this problem. So this approach can give us a log-logn actually times another log-log-logn. This is because we do another divide and conquer here. Okay, so here are some open problems. So we also made some progress on some open problems. Firstly, the question is that can we get a better number of runs comparison to this logn times log-logn times log-log-logn? So we can shave this log-log-logn factor. So this is a joint work with Rajesh, Sohail, and his student Amir and Kuba from our team. And another question is that whether can we extend this approach to other general metric space? The answer is yes. We make some progress. We can make this algorithm work for the general metric space. But the question is that can we get a constant number of runs? This is still open. We do not know how to do that. So this is the open questions. So I think this is my talk. Thank you.
So
question?
For high-dimensional problems, is there anything known for 1 plus epsilon approximations?
I think there's a lower bound of the Euclidean spanner. If you want to get 1 plus epsilon approximation, then you need space at least 1 over epsilon to the d. So yeah, this is unacceptable because d is very large, right? So d is logn. So yeah.
So let's